Hello again, everyone. Welcome to our discussion of section 2.7, where we will talk about one-to-one functions and their inverses. Those two things are very closely connected. In other words, only a one-to-one function has an inverse. And you'll see this extended into trigonometry for those of you who will be taking Math 127 after this course. Before we start, let me just briefly remind you to please, before attending any class or watching this video, please skim through your textbook, read it, spend half an hour to 45 minutes, or at most an hour reading that section, and then attend the class or watch the video and take notes that would be beneficial to you. And then review your lecture notes and solve all the problems you saw me work on your own without looking at the solutions. Preferably, you would be doing that as you watch the video. And then, of course, complete all homework assignments by the due date and review throughout the semester so you can succeed in this course with the highest grade. Okay. Now, we mentioned one-to-one functions, and only one-to-one functions have an inverse. Now, there is a numerical test for that, which we wouldn't need to do in this course, but there is also a graphical test for finding or investigating one-to-one functions that is much easier, much quicker, and it is much more useful in this course as well as trigonometry, which would be Math 127. So just to take a look at that, the horizontal line test says that if any horizontal line intersects the graph of a function at only one point, then the graph belongs to a one-to-one function. But if the horizontal line intersects the graph of a function at more than one point, then we have a function that is not one-to-one. So let's see examples of that very quickly. So the graphical test of this, let's draw something like this. Like that. So this is a straight line and a horizontal line like that, intersects it at any point at one point only, right? So this is a one-to-one function. Okay. Remember, the vertical line test tells us whether we have a function or not. Remember that, the vertical line test? The vertical line test said, this is in the past, that if a vertical line intersects the graph of a function at one point, or the graph of some graph at one point, then that graph is associated with a function. And we gave examples of that. But if the vertical line intersects the graph of any expression or mathematical entity at more than one point, then the entity we have is not a function, such as a circle, such as ellipse, and things like that, or hyperbola. And so this is a horizontal line test. So horizontal line test doesn't tell us whether we have a function or not. It tells us whether we have a one-to-one function or not. Many functions, mathematical entities or equations can be categorized as a function, but they may or may not be a one-to-one function. So this test tells us whether, the horizontal line test tells us whether or not we have a one-to-one function. All right, so that's a good example of a one-to-one function. Let's see an example of a function that is not a one-to-one function. You've seen this before. So suppose if we have something like that, right? This is a quadratic function, right? The basic quadratic function. Then, so we know this is a function. but when we draw a horizontal line, we notice that it'll cross it at more than 1 point. So this is not a one-to-one function. There are many, many examples of one-to-one function and functions that are not one-to-one. But if you practice with enough examples, you'll see that, as a matter of fact, the quadratic function has, in some cases, an inverse. So what is that all about? The situation is that every time you have a function like this, you can restrict its domain to a particular region where it is one-to-one. So, for example, if we restrict the domain of this same quadratic function to 0 to infinity, in other words, no negative numbers are allowed, right? If we restrict the domain of the quadratic function to 0 to infinity, then the piece we will have is going to look like that. Okay, so this is, let me write this down here. So this is y equals x squared. That's the quadratic function. And so is this one, y equals x squared. But here we are restricting the domain to greater than or equal to 0. If you restrict the domain of a function that is not one-to-one, it's possible that you can make it a one-to-one function, and therefore you're going to be able to find the inverse of this function that has a restricted domain. Okay, just keep that in mind. So this is a one-to-one function. Okay, so now only, why did we talk about one-to-one functions? It's because only one-to-one functions have an inverse. And there's an extensive application of this in trigonometry when you will be taking that course, because in that course, none of the trigonometric functions are one-to-one unless you restrict their domain. So you'll be doing that a lot. For those of you who will be taking the trigonometric course, you will be doing that a lot. You will restrict the domain for the sine function, cosine function, cotangent and tangent functions before being able to find the inverse of that function. Okay, so that's what I mentioned here. Only one-to-one functions have an inverse. And so what is an inverse function? Once you have found the inverse of any function, you have in effect reversed the roles of the independent and dependent variables. So in the original function, you'd have the independent and dependent variable, right? X, Y, namely X and Y. Once you find the inverse, the old X is now Y, the old Y is now X in the inverse function. So that's what I've shown here. So there's a numerical and graphical relationship between a function and its inverse. So here you have the numerical relationship between functions and their inverse. So suppose you have a function such that it generates these results for each value of x that are shown, right? For x 10, 20, 30, you have the function value -5, -15, -25. Now, once you find the inverse of that function, which surely has to be a one-to-one function, then the roles of the independent and dependent variables are reversed or swapped. So what used to be the dependent variable, or f of x, is now the independent variable x in the inverse function. Okay, I hope you're catching the differences between the notations here. So -5, -15, -25, they were the y value or f of x value. Now they become the x value in the inverse function. And for all of those values as x, you have 10, 20, 30 as the y value, or the value of the inverse function. So any inverse function reverses or swaps the roles of independent variable with the dependent variable. So how does that look graphically then? Graphically, you have, first of all, I want to attract your attention to the dashed line that you see. That dashed line is the line y equals x. As a matter of fact, you can see it here. It's tiny right there. So let me write it a little larger here. That dashed line is y equals x. Why is that important? Because that line dissects the xy plane, into two equal halves. Okay? Now, whenever you have a function, let's say this f of x, right? So if f of x is this, has this graph that you see on here, then the inverse function has this graph, which is the image of this graph of the original function across the y equals x line. So let me say that again. Graphically speaking, the inverse of a function is the image of the other function, the original function, across the y equals x line. So whatever, and this example shows that, is another example of what I said, which is f of x is that curve, and the inverse of this function has this graph. So this graph, or the graph of the inverse function, is the image of the graph of the original function across the y equals x line. Now, so we talked about two very important connections between the original function, or any original one-to-one function, and its inverse. One connection is numerical. So the numerical connection is that the roles of the variables are swapped. So whatever the value of x is now the value of the y in the inverse function. And whatever the value of the y in the original function is the value of x in the inverse function. So that's the numerical connection. The other connection is graphical. So the graph of the inverse function is the image of the graph of the original function across the y equals x line. Okay? So now, if somebody claims that they have two functions that are inverses of each other, how do we prove that that's in fact the case, or how do we disprove that claim? So last time, in section 2.6, we learned about composite functions, right? Composite functions are functions where you embed or place one function inside another function. So we'll do that to show whether two functions are inverses of each other, and as a result, we would expect to get x. Always we expect to get an x, just x, with nothing else attached to it, if in fact two functions are inverses of each other. So what does that mean? That means if you suppose we have two functions f of x and g of x, right? Suppose we have these two functions, and somebody claims that they are inverses of each other. How do we show or prove that this is the case or it's not the case? Well, we take the composition of these two functions in both directions, not just in one direction, in both directions. So this what you see here at the bottom is critical. So we take the composition of f and g in this direction, and we should end up with x. And so if this happens, we cannot stop. We need to find the composition of these two functions in the reverse direction. So now composition of g and f. Notice composition of f and g, and then g and f. we should get x. Only if we calculate the composition of these two functions in both directions, f and g and f, and we get x in both cases, then we have shown that the two functions that were claimed to be inverses of each other are in fact inverses of each other. Okay? As a matter of fact, we're going to do that in the examples we have. Okay, so how do we find the inverse? Once we know a function is a one-to-one function, then we know it has an inverse. Then how do we find its inverse? Well, it's very, very procedural. As a matter of fact, everything we do in this class, I'd say at least 98% of it, is very, very procedural. So the procedure for this, finding the inverse is, first, replace the function notation f of x with y. Okay? Then second, swap only the variables x and y in the equation you have. This means don't swap their coefficients, just the variables. Okay, so if there's a 2 next to x, you don't need to swap the 2 and bring it to the other side. Just replace x with y and keep the 2 where the coefficient where it is. That's what that number 2 means. And then solve this new function for y, and in the final result, replace y with the inverse function notation. So this inverse function notation has this -1 that looks like a power, but it's not a power. This is just like in the real world where we have names for things and for people. In mathematics, we have names, we label things, mathematical entities with names. So if the original function was called f of x, the inverse function is going to be called f inverse of x. So if it was called g of x, the original function, this would be g -1 and x. So this is, but the way you would read it, you wouldn't say f to -1 power x. No, this is not a power. The way you would read this, you would say inverse of f of x function. Okay, that's how we read that. And this letter has to do with which was the letter that was used in the original function. If the original function had the variable h of x, then this would be inverse h of x function. Okay, so now here's our first example. It says if the function, some original function, it's not been given to us, but it doesn't matter. If some original function f evaluated at x equal 4 was equal to 11, or is equal to 11, determine the value of the inverse of that function at 11. Well, we just talked about that the connection between a function and its inverse, right? We said that the roles of the independent and dependent variables are swapped. So if you know that in the original function, if that was the x and that was the y, so in the inverse function, those roles are reversed. So now this is the x. So what is the y then? What is the value of that? The y, the new y in the inverse function is equal to the old x, so 4. Okay? How about this one? I hope at this point you're pausing the video, writing down the answers before you see the video. Okay, I encourage you to please do that. You will exponentially learn, your learning ability exponentially increases if you do that. If you pause the video, do your own work, then unpause the video and look at my solution. So here, and I hope you've done that and you're back to the video. So here, for the value of, in the inverse function, the x was 30 and the value of the inverse function was 15. Now those roles are reversed when we're evaluating the function. So the function at 15, so the y in the inverse function is now x, is the original function. What is the value of the function at x equals 15? It's equal to the 30, which is, so now 30 is the y in the original function, which is equal to the x value in the inverse function. Okay, so the roles of the independent and dependent variables are swapped between an original function and its inverse function. Okay, so number 3 is asking, prove that the two one-to-one functions, f and g, are inverses of each other. That goes back to what I had here, right here. We said to proving whether two functions are inverses of each other or not, we have to calculate the composition function in both directions. If we got x in both cases, and not just in one case, in both cases, then the two functions are inverses of each other. So let's see if we have that here. So I'm going to calculate the composition of f and g. So we have f, composition of f and g of x. That means g of x must be placed inside f, right? So I need to take all of this and replace all of f of x in x, wherever I see it in the original function. So we have that. Wherever you see x, put all of that, replace x with all of this. So we have x minus 7 to 1/3 power cubed, right? Compare this with that. X is gone. Instead, you have g of x, right? This is g of x cubed, right? All of this is g of x. We're placing g of x inside f, okay? And then plus, of course, the 7. Okay, so now let's simplify. This power on the outside, as we learned before in chapter 1, distributes itself or multiplies itself by the power on the inside. So 3 times 1/3 is 1, right? So we end up with x minus 7. The powers are gone. They multiplied to 1, which is there, but it doesn't count, plus 7. So just remove the parentheses because plus is a neutral algebraic sign. So we have x minus 7 plus 7. Well, the negative 7 and positive 7 add up to 0. So we have x as the result of this composition function. Is this enough? No. Let me bring this back. It is composition function in both directions. So this and the composition function in that direction. So let's do that. So and, right? Now we're going to swap the order of the composition of these functions. So g, composition of f. That means we need to place f of x inside g. Well, where can we put that? Only where x is, right? We can't put it where the numbers are. They're fixed. So the variable is the entity within any function that can accept any other value. In this case, it would be the entire f function, f of x function. So we're going to replace x with all of this. So let's do that. I'm going to put a bracket here just to make it visually distinct when we substitute all of f in here. So we have parenthesis x cubed plus 7. That's where so x is gone. Instead, we have all of f of x, right? This is all of f of x, which replaced x. then minus 7, then close the bracket, and the power on the outside. Okay? It's a tedious work. We got to be careful that our substitution is correct. Okay, so now, again, this minus comes after the parentheses. It's not in the front, so we don't have to distribute this negative into this because it's not in the front. It's after the parenthesis. So I can easily remove this parenthesis. So we have the bracket x cubed plus 7 minus 7 with the 1/3 on the outside. Okay, so now on the inside, plus 7 and negative 7 add up to 0. What do we get? We get x cubed, right, to 1/3 power. Once again, the power on the outside multiplies itself by the power on the inside. We get 1, right? So we end up with x again. So compare these. We took the composition function in both directions, and we ended up with x. So yes, so the two functions, so f of x and g of x are inverses of each other. If they weren't, we would get maybe x here but not here. We would get x or 2x or 3x or x squared, something that is not equal to x. Okay? Okay, so now that we've gone through proving how we can show that two functions are or are not inverses of each other, so let's find the inverse of a one-to-one function. This is definitely a one-to-one function because the graph of this is just a straight line, and a horizontal line definitely intersects it at only one point. So it'll quickly pass the horizontal line test. So the procedure to finding the inverse of a function is at the top of this page, right? Right there. So first, replace the f of x notation with y. So let's do that. So instead of f of x, I'm going to say y equals 7x plus 4, right? Number 2, it says second, swap only the variables x and y. This means don't swap their coefficients, just the variables. Okay, let's do that. So that means when I swap x and y, I'm going to keep the 7 and 4 where they are. I'm just going to swap the variables. So x equals 7y plus 4. Okay, so 7 didn't move with x. It stayed where it is, just the variables moved. Then number 3, solve this new function for y. Okay, so let's do that. We have 7y. I can move this to the other side. So x minus 4 equals 7y. We're solving for y, so I'm gonna put this on this side. 7y equals x minus 4. Notice I didn't change anything, but the habit that I have is whenever I solve for a variable, I like that variable I'm solving for to be on the left side. Okay, it's visually it makes more sense to me, and books are written that way too. Okay, so now to solve for y, all we have to do is divide both sides by 7, right? So y equals x minus 4 over 7. So we've solved for y. Then what we need to do? It says number 4, in the final result, which we now have, replace y with inverse of f of x notation. So just replace y with a different notation, which reflects the proper inverse function notation. So we started with f of x. So I'm going to then say inverse of f function is equal to that x minus 4 divided by 7. Please don't forget the connection between the original function and its inverse. The connection is that wherever you have the x variable here, it's now the y variable here. Wherever you had the y variable here, it is an x variable here. Okay? Those values are swapped. It's just we swapped to begin this process or the procedure. We swapped x and y, but that's not just in letters. The values also have an inverse connection. So whatever used to be the x is now y. Whatever used to be y is now x. Okay. Okay, so number 5, here it says, so we have on this page, we have number 5, number 6, and number 7. So at home, you already have, I've already posted all of these worksheets on Canvas for you, blank ones. So please download that, answer all these on a piece of scratch paper, and then come back to the video. Okay, I hope you do that. I'm assuming that you've already solved these and now you're here to watch or compare your solution with my solution. Okay, so the first thing I'm going to do is replace this function notation with y. Then I'm going to swap the role y and x. So x equals 1 over y plus 3. Then I'm going to solve for y. So I'm going to multiply both sides by, because this is a fraction, right? You can cross multiply, or you can either cross multiply because the denominator here is 1. So you can say 1 times 1, x times that. Or you can multiply both sides by y plus 3. Whichever way makes sense to you, it's fine. So I'm going to cross multiply x times y plus 3 equals 1 times 1. So we have x times y is xy plus x times 3 is 3x equals, of course, 1. So keep in mind, we're solving for y, right? Okay, so anytime you're solving for a variable, I've mentioned this before, you need to isolate that variable. Everything you do is in the direction of isolating that variable. So here we have 3x that we need to get rid of and the x. To move or to get rid of this 3x, we can just send it to the other side. When we do that, it changes the algebraic sign from positive to its opposite, negative. So I should come up here actually. We do that like this. Okay, so we have xy equals 1 minus 3x. Now, divide both sides by x in order to isolate y. So y is equal to 1 minus 3x divided by x, right? So the last step, we started with function f of x, so let's replace this y with the proper inverse function notation. So f inverse of x is equal to 1 minus 3x over x. And there's our inverse function. Okay, I hope this agrees with your own solution. If not, please make sure you follow exactly what happened and learn from the comparison between the two solutions. Okay, so here we want to find the inverse of a one-to-one function, this. So let's replace that. I'm hoping that you already have your own solution in front of you. Okay, so y equals x minus 9 over x plus 9. So all I did was replace f of x with y. Now I'm going to swap wherever I see x with y and y with x. So we have x equals y minus 9 over y plus 9. Okay. Now let's cross multiply because we have one full fraction on this side and one full fraction here with the denominator 1, right? So cross multiplying, we have x times y plus 1. This cross multiplying is no different than multiplying both sides by y plus 9. No different. Okay. Equals 1 times 1 minus 9. So on the left, let's distribute We have xy plus 9x, right, after distributing. And then we have y minus 9. So we're solving for y, right? So we have to isolate y. Xy equals y minus 9 minus 9x, right? So I sent 9x, positive 9x to the other side. It was positive on this side. On the other side of the equality symbol is minus. Okay? Now, I have to adjust here because there are two terms that have y in them. So let's move them to one side. Xy minus y equals minus 9. Let me factor that. Minus 9 times 1 plus x. So I just factored those two terms. So, because what would you do in this case? We said whenever we solve for a variable, we need to isolate it. But how can we isolate y if it appears in two terms? What are we going to do? Well, we need to factor, right? So let's factor y out. Y times x minus 1. Factoring is the opposite of the distributive property. So the way you can check your factorization is simply distribute the y into this and see if you get that expression back. So y times x is xy. Y times minus 1 is minus y. So everything is fine. So then that is equal to minus 9 times 1 plus x. And then to solve for y, or to isolate it, we need to divide both sides by x minus 1. So we have y equals minus 9 times 1 plus x divided by x minus 1. Okay? And then at this point, is there anything we can do to simplify things? No, because this is 1 plus x, this is x minus 1. And so all I have to do is replace that y with the inverse function notation. We started with f of x, so I'm going to replace it with inverse of f of x function. So minus 9. You can have correct answers that look different than what I have. For example, this negative that is in front of this product of two terms, you can bring it down and multiply it by what's in the denominator and make that 1 minus x. Okay, as a matter of fact, I will do that just to show you that you can have correct answers that look different from each other, but they're correct. So minus 9 times 1 plus x divided by x minus 1. So this is one possible correct answer. But on your paper, if in your own solution, if you had this answer, or you're also correct. So f inverse of x equals 9 times 1 plus x divided by 1 minus x. If you have that answer, you're also correct. Okay, so what I did here was simply take this negative and distribute it into the terms in the denominator. So now you have that. So you have 1, negative 1 is now positive 1, x is now negative x. Okay, these two look different, but they're the same answer. Okay. I want to double check my result here just to make sure that I did everything correctly. That looks good. And that also looks good. Y minus y, yep. That looks good. That looks good. Yep. Everything should be okay. Okay, so this number 7, I hope again you have your own solution in front of you and you're here to compare it with my solution. Okay, so we have a one-to-one function. Let me replace the function notation with y. 9x equals x minus 4, right? And then I'm going to swap the x and y. So x equals 9y over y minus 4. Okay, now we're going to solve for y. We know that x has denominator 1 here. We know that you can either multiply to get rid of this fraction on this side. You can multiply both sides by y minus 4. Well, let me do that because I did a couple of examples by cross-multiplying. For those of you who might prefer multiplying both sides by y minus 4, I want to do this example like that. So let's do that. So y minus 4 times x equals y minus 4 times 9y over y minus 4. Okay? And then on this side, we have xy minus 4x. On that side, the y minus 4 and y minus 4 cancel out because this is being multiplied by that fraction. So on the right, we end up with 9y. Okay, so just like the previous example number 6, we're solving for y, but y appears in two terms. So we need to bring them to one side. So we have xy minus 9y, right? This was positive on the right side. When I brought it to the left, it switched algebraic sign to negative. This is negative 4x. When I send it to the other side, it becomes positive 4x. Now, what do? We have y, the variable we're solving for, in two terms, right? We need to isolate it, so we have to factor. Okay, factoring, we have y times x minus 9 equals 4x. And then dividing both sides by x minus 9, right? So to solve for y. So y is equal to 4x over x minus 9. The last step, of course, is replacing this y with the proper inverse function notation. So our original function was called f of x. So the inverse of that would be f inverse of x equals 4x divided by x minus 9. Like that. Okay, I hope this is making sense. So here we have problems number 8 and 9 on this page 4 of this worksheet. Please download the worksheet from the Canvas, the blank one, if you haven't already. Solve these two. And so what I'm saying is pause the video, do that, and then come back to see my solutions. Okay? I'm just hoping that by the time we reach the final exam, you have straight A's on all exams, and you get another A on the final exam and end up with a perfect mark in this course. That's my hope, and that's the way to do it. You got to get to work. You got to work out these problems on your own and not look at my solutions or the book solutions until after you've had the chance to write down your own solutions. Okay, so find the inverse of this, just like before. This is square root, which we haven't done already, but the procedure is the same. So replace the function notation f of x with y. Then swap where you see x and y. Swap those two variables. Now we're solving for y, right? So the radical expression is a grouping symbol, just like a parenthesis is a grouping symbol, just like the absolute value is a grouping symbol, just like the fraction line is a grouping symbol. So a fraction line groups all the terms that appears in its denominator. A radical expression groups everything, all the terms that appear under it. So we cannot have the y variable grouped with anything if we're solving for it. So we need to ungroup it. How do we ungroup this? We square both sides. So x squared, and then square root of 5 plus 6y, also squared, right? So on the left, we have x squared. On the right, this 2, and the index of this radical expression is blank, which means by mathematical convention, it is 2. So this power and that index cancel each other. Instead, we have 5 plus 6y. Okay? So now we're solving for y. So I'm going to keep everything the same, but put this on the left. So 5 plus 6y equals x squared. Notice this is the same thing as that, but now the variable that I'm solving for is on the left, which I prefer. Okay? Then, so 6y equals x squared minus 5. Let me bring this down so it's all on the screen, and I'll put the rest of the solution up here. So to isolate y, we divide both sides by 6. So we have x squared minus y minus 5 over 6. Y equals that. And of course, the last step is to replace the y with the proper inverse function notation. We started with f of x, so I'm going to say inverse of f of x function is equal to x squared minus 5 divided by 6. And this is our inverse. This function is the inverse of that. Okay, so their graph should be the graph of this function should be the image of the graph of that function across the y equals x line, as we explained earlier. So that's a graphical connection. And of course, numerically, we know that whatever x value was here is tied to the y value here, and whatever y value was here in the original function is tied to the x values here. Okay? These connections are highly important in terms of understanding what we're doing here. Okay? So it's just not manipulating algebras and dealing with numbers. Please pay particular attention to these connections. Okay. So the last one, and again, I hope you have done what I've asked you to do, which is solve this first, and now you're here to compare your solution with mine, and hopefully our solutions agree at the very end of this. Okay, so let's replace this with y. Then we're going to swap the x and y. Now we're going to solve for y. Once again, just like before, y is part of a group now, which is being created by this radical expression. We need to ungroup this variable we're solving for. And to do that, we will need to square both sides in order to release it from that group. So we have x squared equals 3y minus 5. Once again, let me switch things so visually it looks better, because the variable I'm solving for, I want that on the left side. Okay, like that. So now let's get rid of the negative 5 by moving it to the other side. Now let me make sure that you see all of that. Okay, so I'm going to put the rest of this up here. So we have 3y equals x squared plus 5. Solving for y means divide both sides by 3, right? That's how we isolate y. X squared plus 5 divided by 3. And then now that we have solved for y, let's replace that with the proper inverse function notation. We started out with f of x, so this will be inverse f of x function is equal to x squared plus 5 divided by 3. Like that. Okay? All right. So we have reached the conclusion of another section here. Again, I cannot emphasize more. Throughout this semester, in all the things we do, you must read the book first before you see these and solve all the problems on the worksheets before you watch the video. That's critical in making sure that you walk away from this course with a perfect mark, an A, hopefully. Okay, for now, have a nice day, and I'll see you all later.